But before I do that, I'll come back to that. If the bolt shear strength is not dependent on the pretension, then looking ahead, why do we need to inspect for bolt tension? If my bolts are acting in shear, it's not slip critical connection. You want to pretension them for your own purposes. Don't inspect for them. Don't get into arguments about inspection. You never needed it in the first place. Now, repeat, the pretension that we have in the bolts is the consequence of small axial deformations. I emphasize small. As we turn the nut on, we elongate the bolt, we pull on it, we deform it. The bolt says, hold it, I don't like that, I'm going to resist that. That resisting force is the bolt pretension. Okay? Those small elongations are simply dissipated or relieved as the shear deformations come into play and shear yielding takes place. Let's go back to our figure. There's the figure again that I showed you earlier. And we talked about deformations, shear deformations and bearing deformations, and then stresses. Let's put the shear deformations on there. And so they're like that, eh? That's a good guess. Is that a lot or a little? It's a lot. You wouldn't even be able, if we looked at axial force deformations, you wouldn't be able to see them. These shear deformations are big. That's a good feature. We like that. That's the shear deformation. And that means that excess of shear deformation, I shouldn't say excess, that bountiful measure of shear deformation is the result of shear yielding in that region. That's what it is. And likewise on the other side, which I don't show. So we have two soft zones, plastic soft zones, that say, you small axial deformations that I spent so much time getting into the system, you've gone now, you've dissipated, and so the pretension in the bolt at this point is zero, essentially. I've been trying to show you that, and I hope in a general way you'll think about it. It's confirmed by lots of tests and strain gauge measurements also. We're at the point finally where I'm introducing an AISC requirement, and I kind of compliment myself that I've left it so long. It isn't about the specification rules, it's about the fundamentals. But it's appropriate now to look at the specification rule, in this case for shear strength, and I'll generally write them as LRFD, having made the case earlier that they're the same. You're calculating R sub n, whether you're a allowable stress design person or an LRFD person, you're still calculating R sub n. Same thing. It's going to be the same number. Okay, so I'll illustrate in this system. That's the design shear strength. That's the label. That's the nominal shear strength. I want to elaborate on that. And the A sub B is the cross-sectional area of the bolt. The phi factor, the factor that says we don't know everything, is 0.75 for factor of safety and allowable stress design. And the F sub V, the nominal shear strength, is, watch, 0.62 times F sub U. I did explain that to you, the von Mises yield criteria approximately, the test results, 0.62. Got it? That's the fundamental. Then the specification writers come along and say, but you're going to have to take a 20% discount on that. And I want to comment on that. And so the final result is 0.50 F sub U. So for A325 bolts, I know you're using tables, and that's, I understand. You have to get the work out. I'm using fundamentals. In the tables, you're probably going to look at forces, but they also tabulate the stresses. So the 0.5 times 120 is what you're permitted for A325 bolts, or 60 KSI, or for A490 bolts, 0.5 times 150 being 75 KSI. Okay? The only thing that I haven't really dwelt on that I want to come back to is the issue of the 80% factor that I had to take. So those are the values that are tabulated. They're tabulated for the thread excluded case. If it's through the threads, you have to take discount also. And this one is entirely justified. You don't have as much area. And tests show that this is about a 0.2 reduction, 0.2% reduction, 20% reduction, 0.2. So in the threads or not in the threads, you have to look at the details. And here's some comments. I've already said the first one, the threads in the shear plane, you have that reduction. That 80%, I don't like, how can I say this? I'm not a strong supporter of that. It's the long joint effect, and I understand that, and that's legitimate. We have a long joint. What does long mean? Then we have to take a reduction. The 20% right off the bat is kind of hard on the system. It's kind of a hard penalty. And AISC is looking at that now. I think that for shorter joints, what do I mean? Certainly around, let's say, up to 15 inches long. You have a lot of connections that are in that category. I wouldn't take that 20% reduction. You have to. You're not given a choice, but I'm giving you some background so that perhaps if you get into difficulty, there's the connection that's been designed, a mistake's been made. Do I, in fact, have a little more, I need a little more capacity? Give me a call. We'll work it out. Maybe, maybe not. You know, if I can justify it and you can pay for the bill, sure, we'll work it out. But more seriously, I think they've made that reduction a little too fast. You understand why it's there. The reason it's there is the long joint effect. The long joint effect is not significant for most proportions in the shorter region. It is for the long region. What's the long region? They say, and I agree with this entirely, that if it's greater than 50 inches, there's a 20% reduction. In the case of the AISC spec, it's a further 20% reduction. So this one has to be taken. So this really long joint, the 26 fasteners, if that was my illustration, the so-called long joint effect is significant and has to be taken into account with this 20%. Also, keep in mind, and you don't know this either, the phi value that's there, which is intended to account for I don't know everything, and it has to be there, is 0.75 in this case. And I think that's too high, too. So I put the two together, and that's how I would be able to justify a relaxation. But I have to do that on an individual basis, not on a specification basis, until the specifications change. Also, AISC has studies going on evaluating what the phi value should be, and there's reason to think that it will emerge that the 0.75 can be higher, but you have to wait for that. The threads in the shear plane, so the 80% reduction, pardon me, 0.8, yeah, 80%, 0.8 reduction factor to account for reduced area through the threads. What about threads are in one shear plane and not in the other shear plane? If you know that's the case, and it'll always be that way, meaning it doesn't depend on whether the bolt comes in from the north or from the south, then you just have to take the reduction once. You know, in principle, you only have to take it for the case where the threads are intercepted by shear plane. But in many details, you don't know which direction the bolt will be put in. And it may be that that will say, well, I have to assume that it's in two shear planes. But that may give you some opportunity for savings, too. I've given you a bunch of material now on overview. I'm not going to recapitulate everything. And we've been spending time talking about what are called bearing-type bolts, where shear is the feature in the bolts. We still have things to deal with, like installation and inspection. But let's look at a real structure. Occasionally, I want to throw a real structure in here just to show you that we know what we're doing. At least we think we know what we're doing. I suppose this is a power plant. I don't know what the structure is. It's in the United States. It looks like a power plant. So we've got these pretty significant connections. Are they slip critical or not? I'm asking you that question, and you roll that through your mind. I don't know the answer, but I suspect from what I see, because the joint region has a different color than the other regions, I suspect that these are designed as slip critical. Did I need slip critical? Well, I don't know. It's not a bridge. Are there moving loads or the dynamic loads? I don't know. But I want to build on that a bit too. So here we are. These guys come out and they look at that and they're all serious about it, but those are actually Dwayne Miller's welders, and they didn't bring the bolts, so it'll be a short pause while they go back and get the bolts. But seriously, here's what's happening. And it's in the easiest form. I've got these plates. I've got the clamping force, which comes from the bolt pretension. I've got, let's say, bare mill scale steel, so I've got a slip coefficient that I can look up or derive or something. And I asked the question, the load at which slip takes place will be a function of what? I'm going to write those things down. It's not that complicated. And then I'll explore those. So what do you think? The force at which slip will take place, we talked about that when I showed you that big picture joint, will be a function of what? Well, what are the possibilities? They're not that numerous. The clamping force, the normal force, yeah, I'll put that down. The slip coefficient, well, I assume so. I'll put that down. I'll put them down. And the area, I'll put that down. Okay? There isn't anything else. And you can sit there as long as you want, but that's it. There isn't anything else. Are we okay with that? Well, the fact of the matter is, it's not a function of the area. Now, I take you back mentally to Physics 101, even high school physics. Remember the inclined plane and the block and the string and all that stuff? Way back, that was all set up to show you that the slip coefficient is independent of the area. Don't ask me to explain that further. Why am I saying, why am I trotting that out? It's important to us as installers, inspectors, the structural engineers, the inspection people, to be able to understand that it's independent of the area. So don't fuss around about, I need to check the area or I see some gaps through there. We don't want that. It's not good practice, but we don't have to have it. It's not going to affect the integrity of this connection. So it's independent of the area. If you bring the parts into close contact over most of the connection, and you have to have that in order for there to be a reaction available for the clamping force, then you don't have to worry about the area. So back to the big picture, and now we're looking in this other region. Again, a reminder that I chose this one second because most applications in buildings shouldn't require slip critical. All applications in bridges, logically, will require slip critical. So I don't want to leave the bridge people out. When will we need slip critical? When the load is repetitive. I've introduced that already. Changes from tension to compression. Because fatigue fretting can occur, I'll illustrate that. If a change in geometry of the structure will affect your structure, then I guess you'll have to have slip critical. But with the usual size holes, normal holes, even a high-rise structure, the P delta effect, if you know what I'm talking about, the structure sways, and I've left it as free to slip. The P delta effect for a 20-story building will be less than 10%. It's well within our resolution of our analysis capabilities anyway. So you should have to justify its application. Now, there are certain other cases that are cited in AISC spec, and I don't disagree with them. They're a matter of engineering judgment. Column splices in buildings over such and such a height. So you'll have to go along with those. There's what's happening. I'll just expand on the slip critical for the bridge people. So there was some tests after a long time. Fatigue crack occurred. You can see as one piece, this is pulled apart obviously, as one part slid over the other, this scratching occurs, and that scratching will lead to fatigue striations, that leads to fatigue cracks. Where did the fatigue crack start? Did it start at the hole? That's where you would, I think all of us would tend to say, oh, it started at the hole. Anybody can tell that. Well, it didn't start at the hole. The hole is a really, it's really not a severe fatigue detail at all. It's a very forgiving detail. And in fact, I'd like to carry on with this, but this seminar isn't about fatigue. It started way back there at just some bigger scratches in the surface, and eventually worked its way over to the hole. As far as the bridge people are concerned, then they simply cannot have this going back and forth of the connected material, which causes the scratching, which causes the fatigue cracks. Hopefully you're writing your questions down. So slip critical connections, you have a choice. It's a serviceability thing, no slip under service loads. Or you also have a choice in your specification. This is new in the 2005 spec. You say, I don't want any slip. Let me back up. It's a bridge. I don't want slip under the day-to-day loads. They add a little factor on there. So it's the trucks times a little bit. The trucks are going and going and going and going. We don't want it to slip under that condition. There are certain other cases, though, where you don't, the designer has decided he doesn't want it to slip under the factored loads. Now, this should be a conscious choice on your part. I want to try to give you a little more background information there, because the second case, if you choose it, will be more expensive than the first case. So for bridge people, they can just go ahead. Now, which one do we use? No slip at service loads, that's fatigue, that's the bridge people. No slip at factored loads. The best example one can think of here is you have a type of structure where ponding can occur. So you've got a long span, flat roof truss, ponding. It's in a kind of structure where ponding can occur. And as the factored loads, meaning the working loads build up, it's higher than I anticipated, and you get ponding. We don't want slip to occur at the factored load level either. So there will be some cases where no slip at factored loads will be the criteria. But don't default to that. You know, read a little more on it, justify it, and like some other situations I've described, this should be the exception. And don't forget, you still have to check shear and bearing under the normal situation of working load slip. All right, from first principles, then, that's where I introduced the idea that area didn't come into play. The load at which that connection would slip, the two plates that I showed you earlier, would be the slip coefficient, usually called K sub S or Greek letter nu. The number of slip planes, I didn't state that in the previous case, and the clamping force, in this case, the total pretension from all of the bolts. That's dead easy, isn't it? Here's what how AISC rule is written in the specification. So let's explain these things. There's the clamping force. We know that that's going to have a role. There's the number. There are the number of slip planes. We know that has a role. There's the slip coefficient. We know that. We have still phi to define. We know what that is in principle. D sub u, what does that mean? And H sub SC didn't show up on the slide, so if you're on this page, add H sub SC there, and I'll explain it in a minute. So those things have to be explained. So those modifiers. That modifier is H sub SC is a modifier that has to do with the hole condition. If you have an oversized hole or a slotted hole, you're not going to get as much pretension as you thought you would. I haven't told you exactly. I haven't ever told you what that pretension is. I better tell you. 70% of the bolt ultimate tensile strength. So the A325 bolt, 120 KSI, you have to pretension that bolt to at least 70% of that. And similarly for the A490 bolt. That's a big force, by the way. All right. If you've got a hole that's bigger than the standard hole, you don't have as much material around the edge of the hole to react that large force. So we don't get, in oversized or slotted holes, you don't get quite the pretension that we thought. As I recall, for an oversized hole, the reduction is 15%. So it's there. The 1.13 says or reflects the fact that we get more bolt tension than the minimum. Measured quantities show that we get at least 13% more. Depends on the method of installation. Be more information coming forward on that. But you get at least 13% more. So we may, it's there, we paid for it, so we might as well take advantage of it. So that's why that one's there. Let me repeat. You don't get 70%, you get 70% times 1.13 based on a lot of measurements. And the resistance factor, if you're saying, I don't want it to slip at service loads, that's the bare bones case, the standard case, and the fee factor is 1. In other words, there's no penalty. If you want to take no slip at factored loads, you're going to pay a penalty. The fee value is 0.85. For those of you who are more conversant with limited states design, LRFD, I've given you the safety indices there. So that was a bunch of material. Bolts and tension was one of our fundamental cases, and that's the one we'll deal with next. We'll take the break now, but during the break, take the break, clear your mind, all that stuff, go to the washroom, water your horse. But here's the issue. When you come back in, we're going to ask the question, how would you write a design rule for this? Okay? It's dead easy. So 22, well, by that clock, just after the 8, when the big hand gets to the beyond the 8, okay.